This video showcases a fluid mechanics principle known as hydrodynamic levitation. Hydrodynamic levitation occurs when an upward stream of a fluid, such as water, is able to make an object in its path, which in this case, a ping pong ball, stay essentially at the same elevation. Hydrodynamic levitation can partially be explained by using Newton's second law, as well as the force equilibrium equation. Two more equations that help explain this concept include the drag force equation, which should be equivalent to the upward stream of water, as well as Bernoulli's equation, which considers two different points that the flow of water will hit. All that was needed to create this scenario was a hose as well as a pressurized nozzle. The nozzle allowed a more concentrated stream of water to be delivered to the ball. An interesting thing about hydrodynamic levitation is that you can actually interrupt the flow of water. As long as it isn't for a prolonged period of time, the ball will continue to levitate in the same place once the water returns to it. The stream of water, which was best able to balance the ping pong ball, reached a height of 15 inches, which, when converted to feet, resulted in a height of 1.25 feet. In addition to a ping pong ball, a styrofoam ball was also tested. However, the styrofoam ball proved to be much more unstable and unpredictable within the flow of water. So regarding hydrodynamic levitation, the Bernoulli principle is one of the equations that will be used to determine the velocity coming out of the nozzle. So to solve for that, you need to consider two different points. The first point that we're going to consider is just as the water leaves the nozzle. This is where the velocity will be at its greatest point, and this will allow us to have an unknown in our equation. The second point will be at the very top of the water flow where the velocity stops, where the gravity starts to take control and turn the stream downward. With these points both considered, we'll be able to solve for this velocity. So with the demonstration, the water flow reached a height of 15 inches, which converted to feet is 1.25 feet. Moving over to the Bernoulli principle equation, this is the equation itself, where the pressure of one side plus the density and velocity of the first point plus density, gravity, and height of the first side is equal to the same equation set up for the second point. Our notes for this equation: the height at the first point is 0 meters because that's our datum. The height at the second point is 1.25 feet because that's where the flow reaches before gravity takes over. We have the mass of the ping pong ball for the next equation, and gravity, which is 32.2 feet per second squared. With this equation, since the height difference is only 15 inches, that negates the pressure on each side, because the pressure is atmospheric pressure, and if the height is close enough, it makes it negligible for calculation. Density, you can cancel that out as well, as it appears on each side of the equation and it's constant throughout. So, which leaves us with velocity 1 squared over 2, which equals the gravity and the height of the second point. Because as we discussed before, the velocity at the second point is going to be equal to 0. Solving through for that, let's get velocity isolated. You have the velocity being equal to the square root of 2 times the gravity times the height of the second point. And working through that equation, you're going to get a final velocity of 8.97 feet per second.
So these calculations were done using the ping pong ball because that worked better than the styrofoam ball. But in order for the ball to levitate, the force produced by the water jet has to be greater than or equal to the downward force of the ball. We had two equations to solve for this. First, that the downward force of the ball was equivalent to the mass of the ball times the gravity, and that the downward force is equal to half of the drag coefficient times the density of the water times the cross-sectional area of the ball, and then times the velocity squared of the ball. Solving for the downward force of the ball, we can see that we got 0.1932 pound-feet per second squared. And then rearranging that second equation to solve for the drag coefficient, we can see that we got 5.7 times 10 to the negative third, and that's a dimensionless unit.